Signal processing theory is mostly based on theoretically continuous time signals, but when we have to deal with signals in our computers where we are doing the signal processing, the computers cannot process continuous time signals. It cannot define infinity. That's the basic idea. So we have to discretize the signals and use discrete time signals. In that case, we have to know the Fourier transform and all the basic things what we have in the idea for continuous time signals also in the discrete domain. So what should be the Fourier transform in the discrete time domain? So the basis function for the Fourier in the discrete time domain we have already defined as uk. Okay, that is the basic function, a basis function. So uk is equal to e to the power j 2 pi by n kn. So what is the change that we are taking from the continuous time domain to the discrete time domain? So the continuous time domain, our basis function was e to the power j 2 pi f and t. To convert it into the discrete time, we said it is uk of n. So that is at n. So it is e to the power j 2 pi. What is f? F is equal to now ky capital N and t is n. That's the idea. So we are converting like this. Now if we take this basis, so our basis is a set like this, and this n for the discrete time signal xn, which is defined as some x1, x0, x1 and so on up to xn minus 1. So this is an n-dimensional vector. Xn is an n-dimensional vector. So n varies from 0 to n minus 1. So for this values of n, we should have a basis set where uk should have certain values for n is equal to 0 to n minus 1. So uk as a whole is an n-dimensional vector. Okay. Now the k can also vary from 0 to n minus 1. So we have uk 0 up to uk n minus 1. But we didn't specify the k, right? So what is the k? K is 0, so it's some value. K is 1, some value. So k are the several rows. So we expand on the k, so we actually have a basis vector. Now we express this basis vector in terms of w actually. So we have wk n. So w is the basis vector for our Fourier basis, and these are several wk0 up to wk n minus 1. So we say k is equal to 0 here. So w0. Now we put wk 0 to wk n minus 1 here, and at the end, okay, we are done. So this is a matrix where k is equal to n and so rows n columns. So it's an n cross n dimensional matrix. So the w belongs to a complex domain of c to the power n, that is n dimensional. So this is our Fourier basis vector. This is the entire w that we have to consider. So in the discrete space, we define the Fourier transform as something like this: xk. So we define that xk is equal to xn times e to the power minus j 2 pi by n kn summation of n is equal to 0 to n minus 1. So these are different at specific k. So at k is equal to 0, this is the running sum over this, and this gives some value. So this gives some vector. So at k is equal to 1, this gives another vector. At k is equal to n minus 1, this gives another vector. So as a whole, this discrete Fourier transform xk is also a vector of n cross n. So instead of representing it in terms of the inner product, yes, which is basically the definition that how do we define xk? So xk is equal to the inner product between this wk and the signal xn. Initially that was this, and this inner product is defined like this. Okay, because it's wk conjugate times xn, summation is taken. That's the inner product definition. But now we have realized that these are basically matrices. So how do we note the matrix representation of the same discrete Fourier transform? That discrete Fourier transform in the matrix form is given as x hat is equal to wk Hermitian times x, where x is also the matrix or the signal. X is the vector, the signal. So this basically is the inner product in matrix notation. Okay, what is a Hermitian here? I mean, yeah. So H for Hermitian. So it's a Hermitian matrix of the basis matrix. So basis matrix is Wk and the Hermitian matrix of Wk is Wkh. That multiplied with matrix multiplication of x gives our discrete time Fourier transform, that is DFT, discrete Fourier transform. So this is the idea of DFT. And for the Fourier basis Wk, we have to understand that these Fourier basis or any basis or this set of basis functions are amongst each other, orthogonal to each other. So the basic Wk and Wl inner product is equal to 0 for k not equal to L. They are orthogonal to each other. They are orthonormal basis. And since they are orthonormal basis, they conserve the energy, because in an orthonormal basis decomposition, the idea is this particular basis decomposition shall conserve the energy. So if we conserve the energy, so basically you are saying this thing is equal to the energy of the signal, something like that, or in the continuous domain, but in the discrete domain is something like this is equal to the energy of the signal. So any orthonormal basis decomposition will conserve the energy as a basic idea. And then what is the inverse discrete Fourier transform? So the inverse of this, okay, we have this idea. Now let's just rewrite certain things and then understand what is the inverse Fourier transform. So the Fourier transform is xk, the discrete Fourier transform is equal to xk is the inner product between wk and x. Okay, now that inner product is given by summation, okay, k is equal to 0, n is equal to 0 to n minus 1 xn times e to the power minus j 2 pi by capital N k n. So this is our inner product, and also we say that k, we explicitly say that k varies from 0 to n minus 1. So this is the DFT. Okay, this is the DFT, discrete Fourier transform. And what is the inverse of this DFT? That is the IDFT, inverse discrete Fourier transform, that gives us back the xn itself, and that should be equal to 1 by n. That means it's some average, because it's an average approximation, summation of xk times wk, that is e to the power j 2 pi by n kn, n is equal to 0 to n minus 1, and k varies from 0, 1 up to n minus 1. So if we take this xk times e to the power j 2 pi by n kn, so okay, this xk is expressed as something like this xk, and this is summed up and divided by n. That means we are specifically calculating some average over the entire k space, which varies from, okay, not n, which varies from k is equal to 0 to n minus 1, because it is in the Fourier domain, so k should vary here, and the time should be varying here, or vice versa. I mean, if you are doing an integration on the time domain, you are doing a dt, so an integration on the Fourier domain should do a df. So in the time domain, n represents time, in the Fourier domain k represents frequency in a way. So if we are doing a dt there in the continuous time case and df here, so in the discrete time case also there should be a crisscross relationship as it is. So if it goes as n is equal to 0 to n minus 1 here, it should go as k is equal to 0 to n minus 1 logically, although the matrix operation overall remains more or less logically same. So This is the inverse representative as I was saying. So this is essentially some sort of an average. So we have xk as a vector. Okay, so xk is some sort of a vector for n cross n, and suppose this is k is equal to 0 and this is k is equal to n minus 1, and these are n is equal to 0 to n minus 1. So it is some rows, a collection of some rows. So when we do it, so what we do, we take each element out of the row, we multiply with the complex sinusoidal component, add with another element of the row, another. So we sum up all the elements of the row. How many are there? N. So we divide by n. So we are basically calculating an average throughout this. So we are calculating running sum all throughout this row and making an average of that. And that average is giving us some xn at time instant n is equal to 0. So doing it more clearly is that every row is some sort of a time instant we are taking. So this is row 1, this is n is equal to 0, this is row 2, n is equal to 1, and so on. The last row should be n is equal to n minus 1, and every column should be k is equal to 0, k is equal to 1, and the last row should be k is equal to n minus 1. So every cell has a particular xk, that is the Fourier coefficient. So for the first row, all the xk's represent the n is equal to 0. So we do a running sum over the entire row across all the columns and take an average of it. We basically get xn for n is equal to 0. That is the idea here. Then we move on to the next row and we again do the same running sum and average it. For n is equal to 1, we get xn. So ultimately, we should get a column vector like this of a dimension 1 cross n, something like that, and that is our xn. So that is the idea of inverse discrete Fourier transform. After this, the basic varied properties are all the same for the continuous time and the discrete time. The inverse, okay, so also in the matrix domain representation, I have to say it the same way. So if x hat in the matrix domain representation is equal to W Hermitian x, that is the DFT, okay, in the matrix form. The IDFT should be the opposite of this. So x should be is equal to 1 by n times x times W, something like this. Or 1 by n times W times x hat. So yeah, x hat is the DFT, so is the average. So 1 by n times W times x hat. In this case, how the Parseval's relation holds? So the Parseval relations are like this. The energy for the time domain case is the square norm of xn should be equal to 1 by n times the square norm of xk. So that's the idea of the Parseval's relation in the discrete domain representation of the DFT and the IDFT. And then after the idea of the DFT and the IDFT and the square norm, the Parseval relations, all the basic other properties, they remain the same. So this gives us the spectrum representation in the different formats. I want to expand on some other things. The magnitude and the phase information of every Fourier transform consists of a magnitude portion and a phase portion for any signal, and this is common to both continuous domain and the inverse domain. So what happens is that a Fourier transform xf consists of a magnitude spectrum and a phase spectrum, while the magnitude spectrum is mode of xf. This gives us a measure of the energy of the signal. So it's basically square root of Ex if we take the energy as Ex. So if you take a mod of xf square, this gives us the energy exactly Ex. So energy of the signal contained in the frequency f, or in the discrete case 2 pi by n. So the frequency is f or 2 pi by n. For continuous we will say the word f, for discrete we will say the word 2 pi by n. So the magnitude spectrum gives an idea of the distribution of the energy of the signal, a measure of the energy of the signal according to the frequency, while the phase spectrum is given by angle of xf. Now this phase gives an idea of the alignment of the signal to the complex sinusoid basis. So the basis is what? The basis was uk is equal to e to the power j 2 pi ft. What is this? It is a complex sinusoid. So it has a cos signal and it has a sine signal, some real part, some imaginary part. How the actual signal is aligned with this complex sinusoid, that is given by the phase spectrum, and also in the discrete domain, same idea. So basically this phase spectrum of a signal gives an idea of the actual shape of the signal in the original domain. So that's one portion of the magnitude spectrum and phase spectrum of Fourier transform. Now basically what happens is we do a Fourier transform of a signal to understand the spectrum of the signal. We do a frequency analysis of the signal and the variation of frequencies in the signal. So with this analysis, an entire signal can be transformed into a frequency spectrum, and we only have the information about the frequency, but we don't have information about the time. Okay, so we miss the information about the time. So suppose piano music is being played, and for every note which is played one after another, there are certain frequencies inside it. A frequency spectrum of it will give us the frequency information truly, but it doesn't give us the information about the time and order in which the notes are being played. So if the frequency is not constant and it's varying over time, so we need the variation of the frequency over time. So we need a time frequency analysis of the signal, and in that sense the time frequency analysis is not possible by doing an entire DFT. But before going into that, in computers we implement first Fourier transform. As I said, the DFT is a matrix operation and the size of the matrix is n cross n. So the operation should take a time computation complexity as O(n) square. And the first Fourier transform algorithm is some sort of advanced algorithm which strategically deals with the Fourier basis W in a very advanced manner, such that the computation complexity decreases down to n log n. And if the computation complexity is n log n, that is the first Fourier transform, that is FFT. So this FFT is very much available in the MATLAB when we do Fourier transform. Now moving forward from it, we are trying to say how do we analyze time and frequency both together in a signal. So there should be both time and frequency representation of the signal in the analysis, so we can understand how the frequency can vary over time, how the intensity of frequency changes over time, and that can be done by using a particular component of the spectral analysis in the MATLAB, which is called spectrogram. Now what is the idea of spectrogram? The idea of spectrogram is underlined with the core concept of short time Fourier transform. Now what is short time Fourier transform? So we have to expand on that idea. So STFT is short time Fourier transform. So the idea and the algorithm of short time Fourier transform is that we have a signal xn which is n dimensional. Cool. So from this to this it has n dimensions. So it is x0, x1 up to xn minus 1. The short time Fourier transform is leveraging on the idea that we divide this entire signal into n segments of length n. Okay, how do we do that? So there should be such segments of length n. How do we do that? So basically we are saying that we want to represent the signal as something like xn plus n times n, where m has a length n and it varies like this, and we get x0, x1, xn minus 1, and the very next segment should be xn, xn plus 1 and xn plus n minus 1, and we keep doing this. So x2n, because m varies, so where m varies from 0, 1 until n, so until n minus 1. So we have x2m, x2m plus 2, x2m plus n minus 1, something like this. Sorry, x2n plus 1, yeah, x2n plus n minus 1. Yeah, and it goes on. Now we consider a signal as a whole of length, no, the signal is of length n. That's the idea. That's where I got that. Okay, so the signal is of length L. So we consider a total length of the signal as M, and we divide the signals into n segments of length n each. So if we do that division, and that means how many such segments are possible? It can be that it is L by n. The closest integer to it should be a floor value. So this is the case, and every column has a length n, and the rows are all the n segments, okay, which can be L by n. So it should be something like n cross L by n floor. So this is the dimensionality of this particular representation of the same signal. So we are representing the same signal in a different manner. After this, if we do DFT on each of the segments, that's giving us the STFT, short time Fourier transform. So a DFT on each of the segment means the STFT, S is equal to the Fourier basis or matrix, which is our WK, okay, and the DFT on each of the segments. So this is WK Hermitian x of n plus mm, something like this, and if we do this matrix operation, so we have WK Hermitian times this particular matrix. So as a whole, the short time Fourier transform will have some xk's like this representation only, and this short time Fourier transforms square modulus is basically the spectrogram. So the idea starts from the question of spectrogram. So what does the spectrogram give us? This mod h square is our spectrogram. So this gives us a time frequency analysis of the signal, where it shows how the frequency varies over time, and every column of this spectrogram is of length n. So it shows us these columns are of length, so there is a maximum time samples of n samples. So the time resolution of the spectrogram is n. The idea in MATLAB works as we have a window of certain time, and that window is moved over the signal in a fashion, and the signal is multiplied with the window, and that gives us this thing, short time Fourier transform. So the length of the window, this is the window, that is of length n. So this is giving us the time resolution n. So if we have a higher length of the window, so we can have a finer resolution in the frequency, and if we have a lower length in the window, we can have a better coarser resolution in the frequency, or vice versa. Something like, if we make the resolution in the time better, the resolution in the frequency is coarser, and if we make the resolution in frequency better, the window length increases, so the time resolution fucks up. So the idea is that we have to deal with this particular trade-off of time, frequency, resolution in spectrogram. So the spectrogram allows us to do time frequency analysis of a signal. With a particular time resolution, we can analyze the frequency variation. With a particular frequency resolution, we can analyze the variation. But we cannot take both good frequency and time resolutions all together. That is the idea of spectrogram. So this trade-off is basically coming from Heisenberg's uncertainty principle in signal processing, where if we want to make the frequencies higher resolution, the time resolution fucks up. If we want to time in a better resolution, the frequency resolution fucks up. That's the idea of uncertainty principle in signal processing. But this spectrogram is pretty useful. So what happens in a spectrogram is that we can see the variation of the frequencies in certain time instance. So the piano being played, the notes have certain frequencies, and which note was played after which can be easily analyzed. And also the time resolution has n and the frequency resolution has 2 pi by n. Okay. So in this particular time slice, if we make a better time resolution, in this particular time slice, the corresponding frequency information will be coarse. And if we want to increase the frequency resolution, the window has to be increased, so the time resolution will be bad. That's the idea. So in spectrogram, this trade-off is there, for which we cannot do, we want to make it better. So okay, if a signal is composed of small bursts and it has some long quasi-stationary components, okay, so small bursts means certain changes of frequency, some quasi-stationary components over a particular window of time, okay, components are pretty stable, okay, then we can analyze those components with a good time resolution or with a good frequency resolution, but we cannot analyze with both the resolutions. So this is a limitation of the spectrogram that we need to focus on, and that's why the next analysis that is there beyond that is an analysis of the using the scalogram, which has the energy in a particular different resolution. So the energy resolution can be varied in the scalogram. So the idea of scalogram develops from the idea of complex wavelet transforms. So for that we have to first define the wavelet function, and then the idea of what is a complex wavelet transform, and then we know that the square norm of the complex wavelet transform is the scalogram. So what is a wavelet? So a wavelet h a comma tau is defined as 1 by square root of a h t minus tau by a. That is the mathematical definition behind a wavelet. Now a wavelet can be a Mexican hat wavelet, something like this, and in a 3D representation and something like that. Okay. So this is a very mathematical definition of a wavelet, and from this definition we can understand a is a scaling factor and tau is the time delay. So this wavelet is used in a complex wavelet transform. This is the wavelet basis. So of a complex wavelet transform, CWT of x with these parameters tau and a, and we can write as Wx of tau and a is equal to the inner product between this h a comma tau and the signal x. So this inner product is basically the integration of xt and h a comma tau conjugate dt. That is the idea of any expansion over a basis. That is the very basic analysis formula that we use. So this is the case, or it can be further defined as 1 by square root of a integration minus infinity to plus infinity xt h conjugate of t minus tau by a dt. So this is the complex wavelet transform. And if we take a square of this, so mod of CWT square is basically the scalogram. Now scalogram literally relieves us from the uncertainty principle of spectral analysis, and it gives us a chance to change the resolutions in both cases, and we can analyze the signal in a better way. While this mathematical definition represents this, we must understand how we can invert this. There should be some synthesis of this scalogram. So the synthesis formula will likewise follow. If we delete these old portions, the synthesis formula likewise follows as the signal can be represented into again the same form, given this synthesis formula CWT x tau comma a times h a comma tau t. Okay, since it is varying over a and tau, the synthesis should have a double integral where a is equal to 0 to infinity and tau varies minus infinity to plus infinity, and there is 1 by ch, and this is d tau divided by a square. So this is the synthesis formula, and in this synthesis formula there is a particular constant, that is 1 by ch, and that constant 1 by ch, where ch is given as that it is the admissibility constant. So ch is equal to admissibility constant. Now what is this admissibility constant by definition? This is my own note. So ch is equal to integration 0 to infinity mod of hf square by f upon f df. Okay. That's the admissibility constant. A lot of math behind it basically. So what is hf? So if we have the wavelet function ht and it has a spectrum hf, that is a Fourier transform over ht. That is the Fourier transform of the wavelet ht. So if we do this mod of hf square df, that is basically the area of the signal in the spectral domain, but divided by f is there also. So this basically gives us the idea of the ch, which is the admissibility constant. But we have to understand, okay, this is a constant, yes, which varies over the frequency spectrum of the wavelet itself. So there this 1 by ch is there. This 1 by ch has inside some variation over the frequency spectrum of the wavelet. And then we have this double integral and all of this stuff beyond that to get the synthesis of xt. Okay, that's there. That is the synthesis formula. But apart from this very mathematics, I have to understand, okay, and the CWT is given by this 1 by square root of a integration minus infinity to infinity xt h of t minus tau by a dt. Okay, if a is greater or lesser than 1, so if a is between 0 and 1, this gives us a compressed wavelet, and if a is greater than 1, this gives us a stretched wavelet. So with compressed wavelet, it can be compressed, and greater than 1, it has stretched wavelet. So whatever it is, so this, the square norm of this is our scalogram. The square norm of it is the scalogram. So signal analyzer will perform certain steps. So what does the signal analyzer do? It divides the signal into many segments and then it computes the CWT. So in the spectrogram we are dividing the signal into many segments and we are computing the DFT of every segment, and that gives us the spectrogram. But in the scalogram case, we are dividing the signal into many segments, and then we are computing the complex wavelet transform. Sorry, I am saying complex. It's continuous wavelet transform. Sorry for the wrong terminology. Continuous wavelet transform. So we are computing the continuous wavelet transform of each of the segments, and then each segment by segment the scalogram is displayed. So since the scalogram follows an orthonormal basis decomposition, it shall preserve the energy of the signal. So the idea is that there is an orthonormal basis decomposition here. So the very word preserving the energy of the signal means this minus infinity to plus infinity a greater than 0 CWT mod square d tau by dA d tau. Also there was a dA here, I forgot. dA d tau by a square. This is the energy of the signal Ex. So the energy of the signal can also be obtained by this particular integral. So scalogram describes how the signal energy is distributed over time with the frequency scale, and the energy of the signal here is distributed with different. So you see this particular relation, the energy of the signal is given by a scalogram. So we can say that the energy is distributed over several resolutions. So this particular scalogram gives a various description of the energy. So energy distribution idea is given. So we can change the resolution for that. So that's the idea of scalogram.